Hello everyone, welcome to this video. In the previous video, we have learned about positive operators. So if you remember, any operator which is defined on some given complex Hilbert space which is bounded and self-adjoint, that operator is positive whenever and we denote positive operator by t greater than equal to 0 operator sign. This is the 0 operator and not the simple 0. Whenever we have the inner product of tx with x as greater than 0, right, greater than equal to 0 for all x belonging to the Hilbert space. Now in this video we shall be studying about the properties of positive operators. The first property here, it states that whenever you have two positive operators and you add them, then the resultant operator is also positive in nature. So how this is possible? Let's see it through this expression. If we consider t1 and t2 as two positive operators, then in that case, by the definition, t1 would be greater than equal to the 0 operator and t2 would be greater than equal to the 0 operator, right? So when you add both of these, what will you get? So we may add both sides. So we, on the left hand side, we may have t1 plus t2. On the right hand side, it is 0 operator plus the 0 operator, which is obviously the 0 operator. So you have t1 plus t2 as greater than equal to the 0 operator. Therefore, from this expression, we can say the sum of two positive operators is also a positive operator. Next, moving on from sum, what can we say about the product of positive operators? This is the second property and this is the second result here. So in order to talk about the product of positive operators, we have this result. It states that if we have two bounded self-adjoint linear operators, let's call one by S, another one by T, which are defined both on the given Hilbert space H, and both of them, they are positive in nature. So all these things are given to each other, and in addition to that, we are also given commutativity. That means both these operators, they commute with each other. That means we may write, instead of ST, we may write TS. There is no difference between these two things. If all of these things happen simultaneously, that means the two operators, they are bounded, they are self-adjoint, they are linear, they are positive and defined on the same Hilbert space, and moreover, they should commute with each other. If that is so, then we can say the product ST, that is also a positive operator. Let's see how. So for this, we need to see its proof. So first of all, we in this case wanted to prove that ST is a positive operator. So what we'll be doing in order to show that this ST is a positive operator, we shall be showing that the inner product of STX with X is greater than equal to 0 for every X belonging to the given Hilbert space. So this is what we will be proving here. Now here again we have two cases. First of all, if our operator S is identically a 0 operator, this is not exactly 0, this is the 0 operator. In that case, the result holds. Why? Because we would, in this case, would be taking the inner product of 0x with x, which is obviously greater than equal to 0. So that means the result would hold in this case. So obviously the product would be a positive operator. But what if the operator is not 0? What would happen in this case? So let's see the result here. So here we shall be proving our result by proving these two things. Firstly, we'll consider for the given operator S, which is now a non-zero operator, right? We can define another operator S1 here, which is nothing but the unit operator here. So the operator that is divided by its norm. So we have S1 as the new operator, and S2, S3, S4, S5 and so on, they are defined through this recurrence relation, this iterative relation. So that means when you substitute n is equal to 1 here, what you will be getting? You will be getting S2 here. So S2 would be nothing but S1 minus S1 square. what would be S3 when you substitute n is equal to 2 in this expression. So it would be S3, 2 plus 1, that is S3, that is equal to S2 minus S2 square. Similarly, when you substitute n is equal to 3 here, you would have S4, that is S3 minus S3 square. And similarly, S5 would be S4 minus S4 square. And in a similar way, we can continue, and we have all the S1, all the S2, S3, S4, S5, S6, S7, S8 and up to infinity from the given operator S, because using this S we are defining S1, and from there onwards we have a recurrence relation which defines these operators. So in this case, we assume this thing that this is the construction, and we'll prove using induction that all these operators Sn, they are positive operators. So that means they are greater than equal to the 0 operator, and moreover all these operators, they are less than equal to the identity operator. So this result firstly we'll be proving, and then using this result we'll prove our main result, that is the inner product of st with x, that is greater than equal to 0. So in the second part we'll be basically proving st is a positive operator. Okay, let's proceed on to prove first part A. So here our aim is to prove that all the Sn, they lie between the 0 operator and the identity operator, and we'll prove this result using induction. So here we'll be applying induction on this number n, right? So whenever we have n is equal to 1, in that case the results hold. Let's see how. The assumption that S is a positive operator. We already know S is given to be a positive operator in the very starting of this result. That is S is a positive operator. That is a given assumption for this proof. So the assumption that S is a positive operator, it implies that S1 is what? S1 is S divided by S norm. Norm is always a positive quantity, you know, and this is a positive operator. So that means this S1 is also a positive operator. This is also greater than equal to the 0 operator. And moreover, S1 is less than equal to identity operator. How this thing is obtained? We'll obtain this thing using the squares inequality here, and the inequality that the norm of Sx is less than equal to the norm of S multiplied with the norm of x. So here we have the inner product of, so we'll prove this thing that S1 is less than equal to identity operator using the inner product. So we'll be proving that the inner product of S1x with x, that is less than equal to the inner product of Ix with x. So this is our aim here. So in order to prove that, we are considering the inner product of S1x with x. Now what is the definition for S1? It is this one, right? So we'll be substituting S divided by, so instead of S1 we'll be writing S divided by the norm of S. Now because this is a constant quantity, it could be taken outside the inner product. So that means we have shifted this one outside. So we have the inner product of Sx with x. Now because here we can use quartz inequality, and according to that it states that whenever you have the inner product like defined like this, the inner product of Sx with x, that is less than equal to the norm of Sx with the norm of x. This is the squares inequality, and here on this expression we may again use this inequality here, right? So this thing is equal to this thing, and this thing is obviously less than equal to this thing. Now you see you have the norm of S here, the norm of S here, they both cancel each other, so we'll be left with norm of x square, and you already know using the properties of norm that norm of x, that is equal to the inner product of x with x, and you can write the first x as identity times x. There is no issue, because whenever you apply identity operator on any vector here x like this, so you'll be having x here. So finally we have just proved that the inner product of S1x is less than equal to, right, the inner product of Ix with x. So that means the operator here this one S1 that is less than equal to the identity operator. So that means the result for n is equal to 1 is done. So next, in the process of induction, we assume that the result holds whenever we have n is equal to k. So that means, what does it mean? It means that all the operators sk, they lie between the positive operator, zero operator, and the identity operator here. So if we wanted to, from this result we can make out another result, how we can have the negative of all these operators. So it would be 0 minus 0 operator greater than equal to minus sk operator greater than equal to minus identity operator. And now we can subtract identity operator on both on all the sides. So it would be I minus sk greater than equal to I minus I. So this I minus I is obviously 0, right? This is I minus sk, and here we have the identity operator. So this inequality we have generated through this inequality here, right? So that means you have 0 less than equal to the identity operator minus sk, which is less than equal to the identity operator. So we have this inequality here in the case of n is equal to k. Now here we wanted to prove that in the next part of induction, that the result holds for n is equal to k plus 1. Now in order to prove this thing, let's see how we proceed in this case. So here we assume that sk is a self-adjoint operator, and for every x which is a member of the Hilbert space, we may write skx as some other member which we are calling as y, right? So here we for case n is equal to k plus 1, we wanted to make out that the operator sk plus 1 is greater than equal to the 0 operator, and it is less than equal to the identity operator. This is our aim here in this particular case, right? Now because sk, all the operators, they are self-adjoint operators. So and moreover, when you apply sk onto x, you have y here. So here we may write we may take the inner product of sk square multiplied with identity operator minus sk xx. Now because this sk, now why we are doing this thing? Because we'll be using all these relations further in order to prove our main result, this one. Okay, so let's see how this thing works. So first of all, we are taking this inner product here. Now because sk is self-adjoint, so we may shift this sk to this side. So what we are left with? We are left with I minus sk, skx, skx, right? And we have also named this skx as y here. So that means this thing is y, this thing is y, right? And I minus sk, this operator is greater than equal to 0. Let's see how. From n is equal to k part, we have this operator greater than equal to the 0 operator. So that means its inner product is also greater than 0. So the inner product of I minus sk applied onto any element y with the same element y is always greater than equal to 0, right? Using this result here. So that means we obtain here that this inner product is greater than equal to 0, right? If this inner product is greater than equal to 0, 0 here is the number. In that case, the operator, this operator sk square I minus sk, this is a positive operator. So let's call this as equation number 1 here. Similarly, in a similar manner, because this I minus sk is also a self-adjoint operator, so using this same calculation here onto this sk I minus sk square, we may have this as a positive operator again. So let's call this as equation 2. How you can prove this thing? You can take the inner product of sk I minus sk square onto some element x and x. Now you can shift this thing to this side again using the self adjointness, and then use the same result here in order to prove that this is greater than equal to 0. Right, so now you have two equations, two inequalities, inequality 1 and inequality 2. So we may add both of them. So what do we have on the left hand side? You have 0 operator plus the 0 operator, that is nothing but the 0 operator. This is less than equal to this term sk square I minus sk plus this term sk I minus sk square. Now you may solve this and simplify this expression a little bit. So you may have this as common, this as remaining part, this and this cancels. This is the identity operator which you may leave behind. So you are left with sk I minus sk. Then you may open up the brackets here. So you have sk minus sk square. And according to the definition of the recurring relation, let me go back there. According to this definition, sk minus sk square, that is nothing but sk plus 1. So accordingly we have here sk minus sk square, that is sk plus 1 according to the definition. So that means 0 is less than equal to sk plus 1. So we have proved one part of our inequality, that 0 is less than equal to sk plus 1. And now we are left to prove that sk plus 1 is less than equal to the identity operator. Right? So we would have to prove that sk plus 1 is less than equal to the identity operator. Now this thing holds how we can make use of the operation that sk square is a positive operator. When you multiply two positive operators sk with sk, that is obviously positive operator, being the square of any operator. And moreover, you also know from the part n is equal to k from here that I minus sk is greater than equal to the 0 operator, right? So that means I minus sk is greater than equal to the 0 operator. So we may combine both of these inequalities. So we have 0 less than equal to sk square, this thing, plus I minus sk, this thing, right? So you may write I here. Now you are left with sk minus of sk plus of sk square. So this is nothing but minus of sk plus 1, again using the iterative relationship. So we have this as minus sk plus 1. So we have obtained from here that 0 operator is less than equal to I minus sk plus 1. And we may rearrange it a little. We can shift this thing to this side. So you have sk plus 1 less than equal to I. So this is the another part of inequality that we wanted to prove here. So in this case, we have proved that the 0 operator is less than equal to sk plus 1, that is less than equal to identity, using the process of induction on the index, this one. Right? So we have proved this result using induction. Now in order to prove the second part here, we have to prove that st is a positive operator. So that means we have to prove that the inner product of stx with x, that is a positive quantity for every different x which is a member of the given Hilbert space. So according to part A, what do we have? We have defined our S1 like this, S1 square. What was your S2? S2 was S1 minus S1 square, right? S3 it was S2 minus S2 square, and so on. So you see from here, if you wanted to write down the value of S1, so what would be it? You will shift this to this side. So you have S1 square plus S2. Similarly, from here, if you wanted to write down the value of S2, it would be, so this S2, that would be S2 square plus S3. So moving on and continuing like this, so you have S1 written as S1 square plus S2 square plus S3 square and so on up to Sn square, and the last term would be greater than this index, because whenever you have S1, that is S2, whenever you have S2, you have S3, so whenever you have the last term Sn, so you would have n plus 1 here. So S1 is written as s1 square plus s2 square plus so on up to sn square, and the last term is sn plus 1. And because all these from in the part A we have just proved that all these they are positive operators, so sn plus 1 is also positive, right? So what would be this? It would imply that all these quantities, if you rearrange this expression a little, this is equal to s1. So this thing here is equal to s1 minus of sn plus 1, right? So from this expression here you have s1 square plus s2 square plus up to sn square, all the sum of squares, that is equal to s1 minus sn plus 1. So we are again using this thing here, and because this is a positive quantity, so therefore if you subtract it from some operator, it would obviously be less than that operator. So s1 minus sn plus 1 is less than equal to s1 here. So let's call this as equation 3. Now moving further to prove this result, according to the definition of this operator here, which is the positive operator, and the self-adjointness of Sj, it means that summation norm of Sjx, here let's see what do we have and how we proceed towards the result. All in all, what do we want? We wanted to prove that the inner product of Stx with x, that is always a positive quantity, in order to prove St as a positive operator. For that we are considering an expression here. This is summation of norm square of Sjx. So that means basically what we are considering s1x square plus s2x norm square up to snx norm square. We are considering this expression. Now obviously you can write each of these norm square as the inner product of s1x with s1x plus the inner product of s2x with s2x, and so on like this, snx with snx. So that is what we are doing. Summation j varies from 1 to n. This norm term could be replaced with this inner product, just as I've told you, using the properties of norm and inner product. And now because Sj is a self-adjoint operator, so therefore you can shift this Sj to this side, so that you would now have Sj square x with x in all the terms, right? Now from above we have just proved that when you add up all these operators here, this is less than equal to the operator s1 here. So instead of all these sj's, the sum of all these sj's, you may write this thing less than equal to the operator s1 here, and here we have x, right? Now so from here you have the summation here less than equal to the norm of s1x with x. Now because n was an arbitrary number, so if we tend this n towards infinity, then we would have this this as the infinite sum also. So this infinite sum is also less than equal to s1, right? So because n was any arbitrary number, and we have proved the result using induction, so the infinite series here, the norm of s1x square plus the norm of s2x square and so on, this series also converges. So in this case we would say the norm of snx, so the last term would converge to 0, and if this norm is converging to 0, the vector, the element itself has to converge to 0 here. So using the third result here, this one, that the norm that the operator s1 square plus s2 square up to sn square, that is less than equal to s1. Using this result again, let's see what do we have. So we have summation sj square x, this sum applied onto x. This is, in place of this thing we may write s minus sn plus 1 using inequality 3, and because Sn plus 1 is a positive operator, this would tend to S1 operator only. Why? Because Sn plus 1 operator is tending towards 0 whenever we have n tending towards infinity. Now all the Sj's, they commute with t. Why? because in the very assumption we have assumed that S and T commute with each other. If S and T commute, that means S1 and T also commute, because S1 is made up of S. Again, S2 is made up of S1, so it will also commute with T, and so on. So all the Sj's, they would commute with T because they are the sums and products of S1, and both S1 is made up of S, and S and T, they are given to be commutable with each other. So that means all the Sj's that would commute with each other. And moreover, because we have defined S1 in the manner that it is S divided by its norm, so from here we may write what is S. S is the norm of S multiplied with the S1 operator. So that means S is nothing but the norm of S multiplied with the S1 operator. So using this thing, using this result here, equation 4, and using that T is a positive operator, and moreover using the continuity of inner product, let's see what do we have here. For every x and for every sjx, which we are calling by yj, j is the subscript. So let's consider the inner product of stx with x. So this is the last portion of calculation. Let's see what do we have. Instead of s, now you may write the norm of S into S1. Why? As I've just told you, X. Right? Now because this is a constant quantity, you can take it outside. So you have the norm of S, inner product of S1 Tx with X. Right? Now because S1 and T, they commute with each other, so you have Ts1 here. Right? And again, you can write this S1 as this limit n tending toward infinity of this sum of Sj square from the expression above, from this equation 4 here, right? So we may have that whenever limit n tend towards infinity, this sum of T Sj square, sum of basically Sj square, where j varies from 1 to n, that tends towards S1. So we have just replaced this S1 with this thing, limit n tends to infinity, summation j varies from 1 to n of this Sj square, right? Now because Sj is a self-adjoint operator, you can shift one of it to this side. So that means you have Tsjx and you have Sjx. And moreover, we have named this Sjx as y here. You can see this thing here, all the sjx, they are yj, so therefore we may, instead of sjx, write yj, instead of sjx, write yj here, right? And this thing is greater than equal to 0. Why? Because if you see this, what is this? This is the inner product of T applied onto some operator yj with the same operator yj, and in the very beginning, because we are given T as a positive operator, so that means this thing, the inner product is obviously greater than equal to 0. So that is what we are doing. This inner product is obviously greater than equal to 0. This norm is always a positive quantity, being the distance. So therefore we have the inner product of stx with x, which is greater than equal to 0. So this implies that st is a positive operator, and this is what we wanted to prove here in this video. So I hope you understood the proof here. Proof was a little lengthy, however the result is quite simple. It states that whenever you have the product of two positive operators that is also positive, provided the operators should be bounded, self-adjoint, linear, positive, and must commute with each other. And obviously we have also learned that the sum of positive operators is positive. Well, that is it for this video. Thank you for watching.